Let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully, you guys are doing well. My migraine's not gone. It's one of those big ones, like not even sleep can take care of it. You just got to ride it out. But let's actually continue. Maybe it's because I'm upset about these 2% fees we're paying these money managers, huh? Come on. Like, what the hell? They're stealing our gains. I'm upset about losing my gains. Okay. I can see the chat and we're good. I think we're good. Okay, so this is what we're going to do today. Let's just do a quick recap of what we did yesterday. Well, we heard that Gauss story, but that was just to make me give some background into the derivation of this formula. But really what you had to know was this formula. So this was the future value of annuities formula. And an annuity was just a fixed sequence of payments. Someone else is coming in here. Basically, this is if you're making certain payments PMT every period, and this is the interest you're being charged. R is the interest you're being charged. N is the compounding rate. This is the future value you can get, basically. So this is the formula we're going to use today, just solving for the PMT instead of the FV. And we actually saw the use of this formula. So the idea is we're not just depositing money at once, one lump sum, just give a bank $1,000 and then walk away and forget it. No, we're repeatedly making the same payments, and we want to see how much we add up to. And then we saw some, at least the first time I saw these calculations, I was like totally taken aback by it. Yeah, you can become a millionaire with $1,000 a month. Takes a long time, don't get me wrong. Probably going into business is much quicker. Well, for sure, if you go into business and you're successful, it'll be much quicker to $1 million. But this is something that you could kind of just have running in the background and not even worry about it. And even if you don't become successful in business, you'll end up a millionaire anyway. So that was very interesting. We also looked at just how a 2% decrease in interest rate, which let's say you're paying 2% in fees to someone else, can actually cause a drastic difference. And then we wanted to actually do an example where we use that same formula, but in terms of a sinking fund, which is where we are now. Let's see where we are now. And picking up from last time, I don't think I actually specifically defined what a sinking fund is. Maybe I should do that. Maybe I should do that. Tell you guys what a sinking fund is. Okay, so definition. A sinking fund is an account into which you make regular payments in order to meet some future obligation. So like a college fund is a sinking fund, for example, right? So there's some future obligation you wanted. You want to be able to send your kids to college in like when they're 18. And so you put money into a college fund. That's an example of a sinking fund. Example, a college fund. And I guess you can think of it as just a retirement account is also a kind of sinking fund. Retirement account, I guess. Although that can get complicated, so. Sometimes, asterisks on that one. But the idea here is that there is a specific value that you have in mind. And that's what I want to get at, i.e. there is a specific FV you have in mind and you want to know, someone else coming in here, and you want to know what your PMT should be, what payments should you be making in order to achieve that? So if you're just randomly saving, that's a saving account. I'm just saving for a rainy day, some arbitrary amount, just trying to, have a cushion. But if you have a very specific value in mind, I need this much money at this time. And right now you want to know, if I know how much interest I can reasonably get, what should my payments be to make that much money at some point in the future, right? That's called a sinking fund, okay? So that's the example that we want to do. So let's say you just have a kid, 18 years from now, you want to send them to Colombia for 2 years, right? You need 150,000. Hopefully the tuition won't rise by that time, but it probably will, let's be honest. Okay, so I want $150,000 18 years from now, okay? Let's say somehow I find an account that's going to give me 5% APR compounded monthly. By the way, I saw a credit union account the other day that was giving you like 6% per year. Like crazy. That's crazy. Whatever, I digress. Let's say I have an account that promises 5% APR compounded monthly, right? So I know I can get 5% compounded monthly. Let's say I trust them that they will maintain this interest rate for 18 years. Not realistic, but let's say, just for argument. What should I be paying into this account every month in order to achieve the goal? Let's assume I don't have $150,000, right? I can just make a few $1,000s a month maybe that I can put towards this goal. What is the minimum value that I should be putting into an account so that in 18 years, that account will have $150,000 in it, right? That's the idea, okay? Under these conditions. So I have a very specific value that I want in the future, and I know the time in the future that I want that. What payments do I need now in order to make that happen in a certain interest gaining environment, right? That's the idea. That's what's called a sinking fund, a fund that does that, okay? So recall, last time we saw that your FV was equal to your payments times 1 plus R over N to the NT minus 1 over R over N. And so this means you can actually solve for the PMT. Right? And this is called the sinking fund formula. Okay, so that's what we're going to use. I have this FV in mind. What does my PMT need to be in order to achieve that FV? Right. So that's our formula. So let's see here. I actually, again, I did the calculations ahead of time, even though I'm going to ask you guys to do it because I need to make sure that you know how to do it. Yeah, I mean, let's just actually jump in here.
Mr. Smith?
Yeah.
Are there banks that will guarantee a fixed APR rate over, like you said, 18 years, or
No.
is it subject to change for?
No,
okay.
Definitely not.
Yeah.
Because the interest rate that a bank or someone else would give you, including the interest rate that a credit card or a loan place would charge you, is dependent on a bunch of factors that they don't control. Like it depends a lot on the Fed, what the inflation rate is, what all sorts of things. So remember, they can't promise you a certain interest rate unless they themselves know that their money is growing value at a certain rate. So it depends on their returns. So there are a lot of times where you'll sign up for a savings account and it will start out at a high interest rate. But then after a few years, you'll realize that they send you a message saying, oh, we're dropping the interest rate by 0.5% or whatever. It's because the environment has changed. So no, it's not. It's not in general a good idea to make a plan on a specific interest rate over a very long period of time. It's not realistic. Um, so there is some approximation. What you can do and what has worked is rather than looking at what interest rate you get now, you want to look at historical interest rates. So, and that's why the stock market is so powerful because we have long records of it. Like I know how the stock market has been doing for the past 100 years, so if I can say, well, over the last 50 years, the average interest rate this market return was blah, then I would use that in my calculations, So yeah, I don't know what the specific number would be from day to day at a particular firm now. It's not going to stay the same. For sure not. Yeah, because it depends on other things. How the country's doing, how the economy is doing, what the Fed or whatever money management government agency they have making decisions. But yeah, but we're just keeping it simple for the purpose of this class. So here, I know that my future value is going to be 150. My interest rate, we're assuming I can get 5%. I'm going to assume that I can get that for the next 18 years, which my time is 18. That's what that means. And it's compounded monthly, so N is 12. What you can also do is you can also just do calculations for a lower interest rate. So let's say someone says, you know what, I'll give you 7% interest rate for the next 18 years. I'll do my calculation with 5. Because chances are, in 18 years, something's going to happen where you're going to have to, remember I told you about 7%? I'm going to have to drop that to 6. And then, now I'm going to be in trouble. My kid can't go to Columbia anymore. Yeah, no. Okay. So here, we would just have our PMT. It's going to be 150, 1, 2, 3. Over 12 over 1 plus 0.05 over 12 to the 12 times 18 minus 1. So that's what our payments should be to achieve that. And you guys can tell me what you get. And right after that, we're going to move on to the next section, which is the main topic of today, 3.4. And is this the last thing in chapter 3? I believe so. So do those calculations and let me know, and let me double check on that. Yeah, so 3.4 is the last thing we're going to do in chapter 3. So it's possible we can finish that today, but I'm not going to force it. So that might spill into a little tomorrow. So definitely by the end of this week, you guys should be able to do all the homeworks for chapter 3. And I would recommend that you do that if you have the time, even though technically it's not due until like mid-March or something. I try to get through the chapter 3 homework as soon as possible. What do we get here? What is that going to cost you? What is $150,000 in the future going to cost you now on a monthly basis? technically that's the wrong way to phrase it. That sounds like I'm talking about present value, but that's not, it's probably not how you want to think about it.
Would it be $429.55?
Yeah, that's what I got. Okay. 429 and 55. That's what it would cost. And of course, if you want to send them for all 4 years, because it's compound interest, it means that it will take a little less than double that to send them for 4 years. And so probably if you can afford to do double that, then you're probably in good shape. Yeah, so that's what it would cost. You want to have 150,000, you find an account that's giving you 5%, it'll only cost you $400 a month. Pretty cool. Okay. And that's the power of compound interest, boys and girls. Okay, yeah. So that's the last example for 3.3. We're now going to move into 3.4. And this is called present value of annuities. And there's going to be something called the amortization formula. But it's really, again, it's the same formula. It's like when I did future value of annuities and the sinking fund formula, they were really the same. It's just when you solve for the other variable, it's going to be the same thing. We're going to find a formula for the present value of an annuity. And then when you solve for the payment value, that gives you an amortization formula. So it's really one thing, but we think of them in two different ways. It depends on what side you're coming from. In another way, this is also turning sinking funds in the opposite way, right? So the idea is when it came to sinking funds, we're worried about the payments we want to make to get up to some future value. But sometimes you kind of want something else to happen. You want to know, how much do I need in order to get payments up to some future value, right? So it's like you want to know the opposite. What lump sum do I need now in order to, for several points in the future, I can withdraw a certain amount of money, right? And obviously, while that money is in an account that's gaining interest, so chances are I need less of a lump sum than I might think in the moment, because it's the money's growing while I'm depositing, right? So that's a very, very different situation, right? So we want lump sum now to get payments in the future, as opposed to payments now to get some lump sum in the future, right? This idea is called the present value of annuities. What lump sum do I need now in the present to get an annuity in the future? Okay, so yeah, let's actually do that. So we're going to build this up, talk about the lump sum case first with the one payment when we just pay it and forget it. Recall, we had that compound interest formula. Okay, we can think of this as the future value, if I put in a present value, can be figured out by that formula. Now, what that means is I can look at what the present value would give me, right? So that would be the future value divided by that, just by, dividing both sides of the equation by this expression, which you can actually rewrite as this guy to 1 plus r over n to a negative power, right? By the laws of exponents that we've covered. So this means that PV equals FV 1 plus r over n minus, and this is a formula you should know. So this is not the formula, the main formula of today. It's just me rewriting a formula that we already knew. So this is the one-time lump sum. Let me put it that way to emphasize. one-time lump sum in order to get some FV in the future. In a compound interest environment. In time t. It's sometimes called a present value formula. But I want to emphasize it's a one-time formula. Right? It's not the idea where I'm continually putting in money, right? So this is the idea where I put it in a lump sum just one time, and in the future I want it to be something, and it's just going to grow and I'm not going to touch it, right? Which is kind of weird. You can't really do a lot with this formula. I mean, not a lot of people would be in that situation where they're like, I'm just going to put a huge lump sum one time. So I'm going to do a silly example at the moment just for you to see kind of where we're going. Okay, yes, there they are. Yeah. But of course, we're going to, with repeated payments, we're going to amplify this this effect, right? Put it on steroids. Okay, so here's a silly example. I want $1,000 in 1 year, let's say, for argument's sake, right? So assuming I can get 5% APR compounded monthly, what can I deposit now so that in 1 year I'll have $1,000, right? So let's say I don't have $1,000 now. I'd like to have $1,000 now, and I'd like to achieve this with like one lump sum payment. Just tell me what money I have to put in an account. Forget it. I show up in 1 year, it's at 1,000, right? It's not a long time. We know this, right? For compound interest to really get going, a year is not a long time. So you're still going to need very close to $1,000 to achieve this, but you don't need the full $1,000 to achieve this. But let's see what we would need to achieve this. We would just use the present value formula that I just mentioned. Okay, so and then I'm going to ask you, how much did that save me? And then we're going to do another example. We're going to say how much that saved us then. So here, what do we know? I know I want my FV to be 1,000. I know I'm getting 5% APR, and I know that I want my T to be 1. I also know that it's compounded 12 times per month. So then what I can do is using, because PV equals FV times 1 plus R over N to the minus NT. And there's going to come a point where I'm going to have to summarize these formulas for you guys and tell you when to use which, but I guess I can actually start now. Why I know to use this formula specifically is because it asked me about lump sum, right? So this is going to be the formula that I use in this context if I know I'm doing a lump sum. If I know I'm doing payments in order to achieve that $1,000, don't use this formula. You need a different formula. Okay, right? In fact, if you know you want to make payments in order to achieve some future value, that's a sinking fund formula. You should be using this formula, right? So you're going to need to know the difference. There's a difference when you're doing a lump sum versus multiple payments. So this is the lump sum idea. That's when we use the formulas that I derived like 3 classes ago, right? So that's how I know to use this formula, because it mentioned lump sum. Okay, so that means if I want $1,000 in the future, I know I am getting 5% compounded monthly, and I want that in 1 year, not a lot of time. How much money do I need? Okay, and I'll just tell you what I got. You can actually verify this. I think I did it. When I did it, I got $951 and 33 cents. Okay. So by doing the lump sum a year in advance, I save almost $50, right? Not a big deal, but hey, $50 is $50, you know. Okay. So how much did we save? We saved 1,000 minus 951. And I didn't do that for some reason, I guess because I thought it was just a subtraction. Okay, 1,000 minus 951.23. So we saved ourselves $48 in this environment. Right. At that point, you probably won't even bother doing it, right? So the trouble I'd have to go through to get almost the money that I want to have only to save me $50, I'd probably just do some monthly installments. But I just wanted you to see the idea of doing it in a lump sum. Okay. All right. So here's the more interesting question, which is what the main subject of 3.4 is. This is far more interesting, right? Yeah, a lump sum that I want to put in now to get like $1,000 payout in the future. Come on, not thinking big enough. Here's a much more intriguing question that you might want to know. What should I deposit now so that I don't just get $1,000 payout, but I get $1,000 every month for the next 5 years? Now we're talking, right? Like I want multiple $1,000 payments, right? So if I can achieve a lump sum now, and that's the present value, which I'll talk about this. Not always is that going to be a lump sum now, but you want to know how much money should you have sitting into an account where you can withdraw $1,000 for a certain period of time while it's growing with interest, so you have enough money until the end of that period. Now we call that the present value because that's what we're starting out with, but technically speaking, it doesn't have to be a present value. Technically, what you could do is, if I know the lump sum that can achieve these payments, what I can then do is set up a sinking fund formula to save up to that amount. And then I know I can just stop saving at that point, and then that will happen, right? So this is something that you can use for planning on the horizon. So for example, let's say, hey, I want to be able to get, when I retire, I expect to live for like 30 years or whatever, you kind of predict when you're going to die and everything. And so you're like, I think I'm going to live about 30 years after retirement. My grandpappy died at 90. His grandpappy died at 90. I'm going to retire at 60. I know I'm going to die in 30 years, right? So you're like, how much do I need to get when I retire? How much do I need in savings so I can get $1,000 a month for the next 30 years, right? That's a more realistic thing. And you're not going to have all that money now, but maybe now you're 20 years old. And so you want to know, by the time I'm 60, how much money do I need in order to achieve this? So at that point, you can set up a sinking fund to get to that. And then you know that you're golden for the rest of the time, right? So that's kind of the idea. So we're talking about present value, but in real life, this would never be something that you're just going to drop all this money all at once, right? So usually you'd save up to this value and then, right? But knowing this value is very important. You need to have that goal in mind. I need this much money to get $1,000 payments for this many times over this period of time, right? That's the idea. This is called the present value of an annuity. Again, an annuity is a sequence of payments. And since you're getting multiple $1,000 payments, you're actually talking about an annuity, right? So that's the idea. So for this, we need a new formula. So I'm not going to derive this fully, but the idea behind the derivation is very similar to the one that we did yesterday, actually. So I'll probably just draw up the diagram and tell you what the formula is without actually doing the subtraction and stuff, because you guys don't have to know it anyway. But if you're interested, you can try to see if you can reproduce it. So the idea is, here is now, right? And here is some time in the future that I can split into. So here's period 1, period 2, period 3, dot, 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 dot. Okay. Does anyone even get that reference when I do it? Does anyone know what I'm doing? I don't know. I'm not gonna lie, I know I'm not so hip. I'm probably doing jokes where they were funny back when I was younger, but this is relatively recent. I don't know. Okay, so this is now, right? And what I want is I want certain payments. So here are the payments that I want, and I want those payments for this entire period. And let's say the regular payments I want to achieve is our dollars, which in our case is 1,000, right? So these are payouts being made to me over the course of this period where I have M cycles. Okay, and M has the same interpretation, right? So then I'm going to talk about, well, what is the present value of each of these cycles, right? What is the present value? Okay, so I know that now what we're going to do is we're going to use this old formula that I just derived in order to get that. So here's how it's going to work. The present value in this situation, in the first one, is going to be 1 plus r over n to the minus 1. This one is going to be 1 plus r over n to the minus 2, 1 plus r over n to the minus 3. And again, don't worry, you don't have to know the logic here. I'm gonna tell you what it is, but minus m minus 1 and r times 1 plus r over n to the minus m. Yeah,
Is
that makes
now
sense.
when they
Okay.
retired?
Come again?
Is now when they retired? Like now?
Yeah,
Is
you can think of now as retirement, right?
okay.
And then I'm getting R dollars per month for M months, right? Now, what is the first one worth, right? So there's some lump sum that happens right here. So so there's a lump sum, right? Now, what is the first payment worth? It's kind of like, well, what value would I need now in order to get R dollars 1 month from now? Well, it's this much, right? Why? Because my T is 1 and my number of times compounded is 1, right? So the very first payment a month from now, that's like this calculation right here, right? It's like my time unit is 1, and this guy is 1 because it's 1 month, and so that's going to be that one, right? Then 2 months from now, what is that? Well, it's now 2. I need 2 units. 3 months from now, that, so on and so forth. And you'll notice that here, it's larger. To get a payment right away, I need a larger amount, right? Which makes sense, right? Based on this example. If I want $1,000 in the short term, I need almost $1,000 to achieve that. That's going to be $950, right? However, if I wanted that $1,000 in 30 years, then no, I don't have to put 900 right now. I have to put less, right? Because it has a longer time to grow. So that's the idea here. This is larger, and this goes down to a smaller, right? So a payment way into the future, I need to actually put in a smaller amount now in order to achieve that payment, right? And as you have a larger negative power, you get a smaller number, right? Again, by laws of exponents. But again, you don't have to know that. So the idea is the PV that I need now is going to just be the sum of these PVs. Right? So then we're going to do that. Then we're going to do that thing where we multiply it by something and subtract, and then by a similar derivation, as with the sinking fund formula. Right. So I'm not going to do it again because, I know you guys aren't a math class, so I'm not going to overdo the proofs thing. But what I'm talking about is if you want for interest to do it on your own, this thing, when I was doing this, right? So I added up all these guys, and then I realized, oh, it's a geometric series, which means I could do this trick, right? Multiply it by R, and subtract one line from the other. In this case, I would multiply by the 1 plus r over n and subtract one line from the other. I'll get something like this that I can solve for with a division. And it will give me, finally, the formula that I'm about to write down here, if you go through that process. So doing that process, you can actually derive this formula. You'd actually get PV equals PMT. Let me just put in the final version, the final form, or maybe not. Okay. I mean, I wrote it down. So you'll get R times 1 plus R over N to the minus M over R over N, which leads to PV equals, the R is going to be what we call the payments. This is 1 minus 1 plus R over N. This is the minus NT. And that's the formula that we want. Word of caution here, because sometimes even I do this, so I'm going to warn you guys about it. Like sometimes I forget that negative. So note, there's a negative on the power. If you don't have that, you get the wrong answer, and it's going to be like way off, right? You need that negative on the power in this situation, okay? So that's the difference between present value and future value. The present value formula, you need that negative on the power, okay? But that's the formula. This is called the present value of annuities formula. And again, remember, whenever I say annuity, I really mean an ordinary annuity, fixed payments, interest being hit at the end of the pay period. Okay, so that's it. So this is, it tells you, gives the lump sum needed to get multiple payments in the future. Now, here's the thing. Of course, you can use this formula for your own purposes. However, in real life, usually what happens is that someone is using this formula against you. So this formula is often used in like loaning situations. So if someone wants to lend you money and they want to know how much to charge you so that they get a certain interest rate, this is the formula they're going to use to charge you. So if you ever wondered, if you go for a mortgage or a car loan or anything like that, and they say, oh, this is the interest rate for this mortgage, and this is going to be your monthly mortgage payment. Like, where did they get that number from? Yeah, I'm borrowing $300,000 to pay for a mortgage, and they're like, oh, your monthly mortgage payment is going to be $950 or whatever it's going to be, right? Where did that number $950 come from? It came from this formula here. So this is also used to talk about how the payments needed to pay off a debt. It's often used in that context. And so if someone says, I'm going to loan you this much money in the present, this is the present value, I'm just going to give you as a lump sum, here's the payments you would have to make in order to pay me back, right? It's often used in that context. And so sometimes we can solve for the other guy. We can solve for PMT, and we get, again, you just do the math, multiply both sides by R over N, then divide by the thing in the square brackets, and you would get PMT equals the present value times R over N over 1 minus 1 plus R over N to the minus NT. And this is called the amortization formula. And again, note, happens to the best of us. It's the negative power. Don't forget the negative power. It's so easy to forget it. There are so many times when you don't have the negative power that you just get, your fingers just get used to not putting a negative there. So don't forget it with this situation. Now, why is it called an amortization formula? Well, for a very morbid reason, actually, because mort, right, is root word mortality equal death, right? The idea here is payments needed to kill a debt, right? That's often how it's used, okay? So there is some present value that you're being loaned under certain interest terms. What payments do you have to make in order to pay back that value? Or in other words, to put the debt to rest, right? To put it to bed, to kill the debt, right? So that's why it's called the amortization formula. But it's the same as the present value formula. Okay, so what you can do is, what lump sum do I need now to achieve certain payments, right? Which is the same thing that someone who's lending you money would be thinking about. Okay, I want to make $500 a month off of this customer who wants to borrow money from me. If I want him to pay a certain interest rate, what loan amount should I offer him now in order to get that back, right? But you can actually use this as well. And I'll show you some examples of where you can use this formula as a consumer. But just so you know, most of the time, this formula is actually going to be used against you. However, the first thing I want to do is to go back to the previous question. And I think we're almost out of time. So this is the last example I'm going to do, which is fine. I will leave the other examples. I have two more examples to do. I'll leave those in the notes for you guys to try them on your own. And then on Friday, we'll go over them together. But I would recommend that you try them. Also, maybe start your chapter 3 homework. Let's go back to the previous question. Is it still in my memory if I save it here? What should I deposit into account so I can withdraw $1,000 a month for the next 5 years? Yeah, sure. Okay, so let's go back and answer this question. We have the technology now, okay? Okay, so does anyone get that reference? $6 Million Man? No, okay, never mind. All right, so what should I deposit now into that account to get $1,000 a month for the next 5 years? So here, and again, 5 years is not a long time. So you're not going to see the real benefits here, but it's going to actually be a lot more significant than $50. So here, what do I want? I want my payments made to me to be $1,000. I know that I'm getting 5% compounded monthly, and the time I'm looking at is 5 years down the road. Okay. Yeah, so this means PV equals PMT times 1 minus 1 plus R over N to the minus NT over R over N. Okay, so this is going to be, I want $1,000 payments, assuming I can get 5% interest rate compounded monthly. So that happens 12 times a year for the next 5 years. Assuming, again, I can get 5% compounded monthly. You do that, and did I do that calculation? Yes, I did. You'll get 5.2, or you should get, so try this on your own for sure. Don't just take my word for it. One of these days, I might just give you the wrong answer on purpose and see if anyone catches me. You never know. I could also just make a mistake. I am human. Okay, so that's what you would need now. How much do you save? Well, the sum of all the payments. Well, that would actually be 60,000, right? You get $1,000 a month for the next 5 years. That's 60 months, and you're getting $1,000 every month for 60 months, right? So that's what you get back, but you have to put in this much. So this means what this account helped me did was to save 60,000 minus 52,990.71. So I saved around $7,000, right? So not anything to sneeze at. And that's just over a 5-year term, which is probably not long. A lot of times, if you as a person, you're using this formula, it's probably for retirement. So you're going to have like 30, 40 years. And so you can definitely save up a lot of money in a short amount of time. But yeah, I would need $52,990 in an account that gains 5% interest. And if I have that, I'll be able to withdraw $1,000 every month for the next 5 years without running out of money, assuming the interest rate stays and everything like that. So that's actually the last example. I will copy the other examples here now. Where do I have them? Yeah. So here's an example that shows you why we call it amortization. So if someone is lending you money, they can use this formula to calculate how much you should be paying them, right? So let's say you want to start a business, you need $100,000. You go and you try to borrow $100,000. They give you 3.99 APR compounded monthly. What do your payments be if they expect you to pay back that 100,000 in 5 years, right? What is your monthly payment going to be, right? You can use this formula. So what payments do you need to kill that $100,000 debt? Amortization formula, right? And again, so that's how it can be used against you, quote unquote. How it can be used for you. Here's another example. Let's say you want to buy a car, and you know ahead of time what payments you can make. So you did your budget and you're like, I can put $450 a month towards a car payment. So if you go into a car dealership and you know they're offering a promotion of 2.99% APR, what price car should you ask for so that you can pay $450 a month or less in car payments, right? To figure that out, you can use the amortization formula. Can you afford a $50,000 car, a $60,000 car, a $15,000 car? Like what car should you ask them to show you? The latest and greatest, or mid-level, or maybe even entry level, right? If you know what payments you can make, how high can you go? So this application is called the max purchase price application. And you can actually use the amortization formula to figure out both of these. So you guys can try those. We'll do them together on Friday and move into something else. We'll start linear programming on Friday. That being said, remember, I'm going to show you guys how to do linear programming with Python and Excel. So get your Python and Excel game ready to go, because as of next week, we're going to be using those. So I'm going to show you how to do stuff by hand, but then I'm going to actually show you how to do it on computer and programming as well. So by next week, have your Excel and Python up and going. Yeah, that being said, we'll stop right there. Unless there are any questions. Okay, all right, that's cool. Have a good rest of your day. I will see you guys again on Friday. Ciao.